Hey, Chem 20s. So we were just talking about polarity, and I wanted to continue on that discussion on polarity. We were talking about one of the practice problems in your polarity note guide, and this magnesium sulfide, of course, the bond between the magnesium and the sulfur, we've got the metal that is magnesium, and then sulfur is a nonmetal. So that definition makes it an ionic compound. But when we look at the electronegativity difference, so we've got magnesium 1.3 and sulfur 2.6 when we look up those electronegativity values. And as I mentioned, the electronegativity difference between those two atoms, 2.6 minus 1.3 is 1.3. So that means that this molecule it acts like a molecule, not like an ionic compound. It falls within that polar covalent range. Remember, we said that is between 0.5 and 1.7. So yeah, even though it is made of a metal and a nonmetal, it actually is going to act like or behave like a polar covalent compound. So here we see the more electronegative atom where the electrons are spending most of their time, and the more partial positive magnesium, right, it acts like a polar covalent compound, even though we know it is an ionic compound. Okay, so next page, there's some questions here that ask you to list and order the bonds, according to increasing bond polarity. That means that you have to look at each of these molecules and determine the difference in electronegativity. And then you're ranking them from the lowest electronegativity difference, the smallest number, to the highest electronegativity difference, and that would be the biggest number. So H2O is our first compound, and obviously H2O, hydrogen and oxygen, it's a V-shaped molecule. So what are the bonds there? Just the bonds between H and O. So you write out the bond H to O, you write down the electronegativity values from your data booklet, you determine the difference or the change in electronegativity. For hydrogen and oxygen, it is 1.2. That means that we have to put this little symbol. That means this is a dipole. We have a polar bond. That value falls within our 0.5 to 1.7 general guideline or rule of thumb that tells us that we have a polar bond. And so the oxygen, because remember, oxygen has those two lone pairs of electrons, so it's very highly electronegative. All the electrons are hanging out at this end of the molecule. That's why we designate it more negative. The hydrogen, though, doesn't have any lone pairs, and so it's the more positive end of the molecule. So the next guy on my little list here, hydrogen gas, this is going to be a non-polar bond. Why? Because hydrogen and hydrogen, two of the exact same molecules, it's diatomic, and the difference between them, 2.2 and 2.2, that there's no difference. So this is a non-polar bond, whereas this guy was a polar bond. So you're going to have to do a little ranking system, and you're going to have to rank which guy is going to be the least electronegative it's got to be this guy, obviously, right? Hydrogen is going to be the least because his electronegativity difference is 0. And then who would be the next most, and 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 so forth, all the way up to who's got the most electronegativity difference, which guy has the biggest number, the biggest difference in electronegativity. Okay, and so that's how you're going to do A, B, C, and D. And for C and D, you're going to have to draw these structures out. So figure out what different bonds are there in this molecule, right? And so in order to do this, you have to basically go through and decide what is the Lewis diagram for each of these so that you can decide what are the different bonds. So we see there's a CH bond in that molecule, there's a CO bond, and there's an OH bond. And then you're going to look at electronegativity, find the difference, and then rank them from the least electronegativity difference all the way to the most for that particular molecule. Okay, so that's how you're going to complete these questions. Now we're going to get on to the discussion of how do we know if an entire molecule is polar or not. Great, we've already talked about looking at the bonds, how much difference the electronegativity is. So to figure out the polarity of an entire molecule, I mentioned this in our last video, you have to look at not only the electronegativities, but also that 3D VSEPR, the stereochemical shape of the molecule, and ask yourself, is the molecule symmetrical or not symmetrical? And so here we have a couple of examples on the next page where we're looking at a few molecules. So we've got carbon dioxide, and I have told you guys that this is non-polar. So why is that? So again, we're looking at two things, the electronegativity difference between the atoms, and we go onto our data booklet and we see 3.4, 2.6, 3.4. So there actually is a bond dipole. This is a polar bond between carbon and oxygen, pointing more towards the oxygen. Why? Because those lone pairs, all the electrons in this molecule are hanging out more at the oxygen end. It's partial negative because of that. On the other hand, look over here, same difference of 0.6, and so that creates a bond dipole that points towards the other oxygen atom again. Why? Because all the electrons are out here in the molecule. So these vectors actually cancel each other out. You've got one guy going this way to the left and the other going equally to the right. That cancels out to 0. So that means that this molecule, even though it has polar bonds, but the molecule itself is what we call symmetrical. And if you kind of imagine the evenness of the molecule, right? You look and you were to split it right down the middle, has an oxygen on either side, it's symmetrical. It's got the same atoms on either side, same electronegativity difference, and this molecule is symmetrical. Therefore, if it is a symmetrical molecule, it is non-polar. So that is why it is a non-polar molecule. Now, I've already talked to you guys a little bit about water, and this is definitely a polar molecule. Like I said, you guys have known that for a long time, since Science 10. So how do we figure it out? Well, two things again. You look at the electronegativity difference between the atoms, and then you have to look at the shape of the molecule. So the electronegativity difference between hydrogen 2.2 and oxygen, which is 3.4, that electronegativity difference is fairly significant, 1.2. That falls in our polar range. We would say that that is a polar bond. And then we draw our little bond dipole. The electrons, again, are more hanging around the oxygen atom and not so much around the hydrogen. That's why it is partially negative around the oxygen end. Now, that's the same thing over here as well. The electrons are around that oxygen atom. This is a V-shaped molecule. And because it's a V-shaped molecule, every V-shaped molecule is going to be polar. These dipoles do not cancel out. So you've got one that goes up here like this, and then the other guy is going like this. And so we can create what is called a net dipole. We get this net dipole. So going from the start to the end and the start to the end, we add up, and this is what we call a net or a resultant dipole. And what does that mean? It means that if you have a net dipole or a resultant dipole, that the molecule is not symmetrical. The molecule not symmetrical, another word for that, means it is asymmetrical. So know what? That means this is a polar molecule. So it had both polar bonds and also a not symmetrical shape. So we are going to call this a non-symmetrical or asymmetrical molecule, and we say then it is polar. All right, what else? Well, here's another example. Why is methane non-polar? So first thing to look at, again, electronegativity difference between the different atoms. Hydrogen, we know 2.2, and carbon, we know, is 2.4. So, sorry, carbon is 2.6, I believe. The electronegativity difference is 0.4. So that's not much of a difference, right? And we also see that this molecule is considered to be symmetrical. Here's the carbon in the center, and all the atoms around it are identical in this tetrahedral appearance. So with identical atoms all around it, the dipoles actually cancel each other out. So you could draw out those dipoles, and you would show that the dipoles cancel out, and that makes this a symmetrical molecule. So this is nonpolar. Okay, so again, two things you look at: nonpolar bond and also a symmetrical shape makes this molecule nonpolar. So when you're asked to figure out, is the molecule polar or not, you've got to go all the way to your Lewis formulas, Vesper diagrams, draw the dipoles, and look to see, is the bond electronegativity, is it a polar bond or not? And then look at the shape of that molecule. So on the next page, there's a couple of examples that I'm going to do with you. So silicone tetrabromide, SiBr4. Well, one silicone, 4 bromine, and that's a total of 32 electrons. So starting right as if you're doing this molecular formula, this Lewis formula, you find the central atom, you make the pairs, and you fill out the peripheral atoms and the central atom, and then you find out what shape is it according to Vesper. Well, this guy has a total of 1, 2, 3, 4 bonding pairs and 0 lone pairs. Silicone is almost exactly like carbon, right? Same group, and so they behave very similarly. Total of 4 pairs, 404. This is AX4. This guy's tetrahedral. So then you draw out your stereochemical, your 3D diagram. And here we have the 3D diagram for this SiBr4. And so looking now, then you determine what is the electronegativity differences. So grab your data booklet out, and what is the values for each of these atoms? What is the value for bromine? Well, bromine 3.0. And what is the value for silicone? Silicone 1.9. So yeah, there's going to be a dipole there. There's an electronegativity difference that creates a bond dipole. We have some polar bonds here. But these, because this is a tetrahedral molecule, are going to cancel each other out. These guys cancel each other out. And these guys, remember, because this is a 3D structure, one goes away from the page, towards you, and then one goes away from you. And so these guys cancel one another out. So yes, there is a polar bond here, but because this is a symmetrical molecule, this is a non-polar molecule. Okay, so again, symmetry generally wins out over polarity of bonds. Okay, so looking at that is going to make it a non-polar molecule. All right, your guys' job is you got to draw these molecules out. Look at the bond polarity. Is there a polar bond or not? Look at those electronegativity differences. Then, is it symmetrical or not? And decide, well, if it's symmetrical, then it is a non-polar molecule. If it is not symmetrical, it is polar, just like water was. All right, have at her, guys, and get in touch with me, michelle.ladine@ghsd75.ca. Take care, and let me know if you have any questions.